So now we're going to talk about balancing chemical equations, and more specifically we're going to be looking at redox reactions. Okay, so how to balance chemical equations for redox reactions. Okay, this will include ionic equations as well as full equations. So the rules for balancing equations are the following. Okay, the first rule for balancing equations is that the number of atoms on both sides, right, of the equation, on the left hand side and the right hand side, have to be balanced. Have to be the same. Right, this is just conservation of mass, right? You're going to have the same number of atoms on the left hand side and the right hand side of each element, right? The number of atoms of each element on both sides of the equation have to be the same. Okay, this rule obviously applies to all chemical equations, right? The next rule that we have is that the overall charges on both sides of the equation have to be the same. Okay, so what we're saying is that the number of atoms of each element have to be balanced, right? And the charges on both sides of the equation also have to be balanced, right? Again, this rule also applies for all types of chemical equations. Now the third rule is specifically for redox reactions. Okay, the third rule is for redox reactions. The rule is that the increase and decrease in oxidation number have to be balanced, right? Or we can say that the gain of electrons has to be balanced with the loss of electrons, right? Gain slash loss of electrons has to be balanced. Okay. Now this only applies to redox reactions, right? Because in redox reactions involve changes in oxidation number, or they involve electron exchange. Okay, whereas the first two rules apply to all kinds of chemical equations, whereas the third rule applies specifically to redox reactions. Okay, so for redox reactions, we're going to be looking at all three of these rules. Okay, and sometimes if you have difficulty balancing equation using just the number of atoms on both sides, we can balance them using charges. And if it's a redox reaction, we can also balance the chemical equation using changes in oxidation number or gain and loss of electrons. Okay, and this is actually the most effective way to balance complicated redox equations. So we're going to be looking at that next. So this means that for a redox reaction, the increase in oxidation number has to be equal to the decrease. In other words, there's no net increase or decrease from on the left and right hand side of the equation, right, in oxidation number. Similarly, we don't write electrons in the overall equation. So the overall gain for whatever is being reduced, okay, of electrons is equal to the overall loss of electrons for whatever is being oxidized. Okay, so they have to be equal. So let's look at a reaction, okay, as an example of how we can use this idea to balance an equation. I'm going to start with a very simple example, okay, which is the reaction of zinc with hydrochloric acid, right? So zinc reacts with hydrochloric acid to form zinc chloride, right, salt and hydrogen gas. So this is a pretty straightforward equation to balance, okay, but we're going to try and balance it using changes in oxidation number or by looking at the loss and gain of electrons, okay? And for that, we're going to write half equations, okay? Now this is a redox reaction, okay, this is a redox reaction. So over here, zinc is the reducing agent, right? It undergoes oxidation, right? Zinc is the reducing agent, it undergoes oxidation, right, from 0 to +2, and HCl is the oxidizing agent, right? Specifically, H plus undergoes reduction, right, from +1 to 0 in hydrogen gas, right? H over here has an oxidation number of +1, and in the elemental form it's 0. So the reducing agent is undergoing oxidation and the oxidizing agent undergoes reduction. Okay. So when we talk about half equations, okay, half equations are obviously, as the name suggests, they're not full equations. They're specifically equations that show what's happening in the reduction part of the equation and what's happening in the oxidation part of this reaction, right? So half equations sort of separate the reduction and oxidation processes in a reaction. Okay, so if you look at the half equation for reduction, right, over here we know that H plus is undergoing reduction, right? So we can say H plus is gaining an electron, right, because it's going from +1 to 0. So H plus is gaining an electron to form hydrogen gas, right? And for now, I'm just going to write half H2, right, to balance the hydrogens on both sides. And we know that zinc is the reducing agent, okay? So the half equation for oxidation, is zinc loses 2 electrons to form Zn2 plus. So over here, this is the half equation for reduction and this is the half equation for oxidation, okay? So half equation essentially shows separate, we have separate half equations for reduction and then we have a separate half equation for oxidation. For a redox reaction, the overall gain in electrons has to be balanced with the overall loss in electrons, right? So we can see that zinc is losing 2 electrons whereas H plus is gaining just a single electron to go from +1 to 0. So what we can say is that okay, we're going to need 2 H pluses for every 1 zinc, right? Since we're going to balance the electrons. So we have 2 H plus 2 electrons, and then we're going to produce 1 H2. We're going to produce 1 H2. So if you look at the overall equation then, right, we have an ionic equation here. We have Zn reacts with 2H plus to form Zn2 plus and hydrogen gas. What we can say here is that for every 1 zinc, we need 2 H pluses. For every 1 zinc, we're going to need 2 H pluses. So this is our balanced equation, right? Using the idea that the gain of electrons has to be equal to the loss of electrons. So we can balance this equation by using these half equations and balancing the electrons. Now another way to balance this equation, okay, is by using changes in oxidation number. Now we know that it's a redox reaction, right? Because we know that zinc is going from 0 to +2 and hydrogen is going from +1 to 0, right? The oxidation number of zinc is increasing, it's being oxidized. The oxidation number of hydrogen is decreasing, so it's being reduced. What we can say is that, okay, we know which particular atom is being reduced, right? We know that hydrogen atoms, right? The oxidation number of hydrogen atoms is decreasing. And we know that it's decreasing from +1 to 0, right? Similarly, we know that zinc is being oxidized, right? So we know that the oxidation number of zinc is increasing from 0 to +2. So what I can say here is that the decrease in oxidation number of hydrogen, right, or the change in oxidation number of hydrogen is -1, right? Whereas the change in the oxidation number of zinc is +2, right? The oxidation number of hydrogen is decreasing by 1, that's a change of -1, and the oxidation number of zinc is increasing by 2, so that's just a change of +2. And for a redox reaction, we know that the changes in oxidation number have to balance. So we can say that we need 2 hydrogen atoms for every 1 zinc atom, right, in order for the overall increase to balance with the decrease in oxidation number. So we can say that for every 1 zinc, we need 2 hydrogen atoms. So we can balance this equation using changes in oxidation number as well. So over here, okay, this is the same idea as we had with the half equations. Okay, what we're saying is that zinc is losing 2 electrons. So the oxidation number is changing by +2, right? It's losing 2 electrons. And we know that each H plus just gains a single electron. Now, if zinc is losing 2 electrons, we need to gain 2 electrons. So each H plus is gaining a single electron. That means each H plus, the oxidation number is changing by -1. So we need two hydrogens, okay, we need two H pluses to gain those two electrons, right? So two hydrogen atoms need to change their oxidation number by -1 to balance the increase in oxidation number of zinc, okay? So that means we need two hydrogen atoms for every one zinc atom. So now let's look at the next example. Okay, the next example says that Fe2 plus ions can be oxidized by acidified manganate 7, okay, acidified manganate 7, right, to Fe3 plus ions, right, to Fe3 plus ions. Mn2 plus is also produced in this reaction. Mn2 plus ions are also produced, okay. Write the ionic equation for this reaction, okay. Write the ionic equation for this reaction. So over here our reactants are Fe2 plus, okay, is reacting with acidified manganate 7. So manganate 7 is MnO4 minus, right? Here manganese has an oxidation number of +7, right? So if you want to calculate that, let's say that manganese has the oxidation number X. We have 4 oxygens and the overall oxidation number is -1, right? Remember, each oxygen is -2 obviously, and that means X is equal to +7, okay? Hence the name manganate 7. So we have acidified manganate. So since it says we have acidified manganate, that also means that we have H plus ions present, right? We have H plus ions present, right? And in the products we have Fe3 plus, okay, Mn2 plus, and then the product missing is, the missing product over here is H2O, okay, because we have H plus and we have these oxygens, right, which aren't shown in the product side. So we have H2O, okay. Whenever you have these polyatomic ions with the 8, right, with the oxygen atoms, these anions, and you have H plus present, you'll also have H2O present as a product. So here again we have a redox reaction, right? Fe2 plus is the reducing agent, right? It's undergoing oxidation. The oxidation number of iron is increasing from +2 to +3, right? The reducing agent undergoes oxidation, and manganate 7 is the oxidizing agent, right? It's undergoing reduction. The oxidation number decreases from +7 to +2. So we're going to balance this equation. We're going to write half equations first, okay? Now, let's write down the half equations. So now if we write down the half equations, we're going to have the half equation for oxidation and the half equation for reduction, right? Now the half equation for oxidation here is the oxidation of Fe2 plus, right, to Fe3 plus, right? The equation for that, right, because we know that Fe2 plus is undergoing oxidation. So the half equation for oxidation is Fe2 plus loses an electron and forms Fe3 plus. And now if you look at the half equation for reduction, right, we know that manganate 7 is the oxidizing agent, it's undergoing reduction. So we have MnO4 minus, right, acidified MnO4 minus, acidified manganate 7, so in acidic conditions, right, and we also know that its oxidation number is going from +7 to +2, right? So that means that each manganate is gaining 5 electrons, right? Its oxidation number is decreasing by 5. So we have plus 5 electrons to form Mn2 plus and H2O. The oxidation number of manganese is decreasing by 5, right? From from +7 to +2. So the change in oxidation number is -5. So it's gaining 5 electrons. Okay, and since it's acidified, we also have to write down H plus. Now this half equation obviously isn't balanced, right? Because on the left hand side we have 4 oxygens. So on the right hand side we also need 4 oxygens, right? And then we have 8 hydrogens on the right. So that means we're going to have 8 hydrogens on the left. So this is the half equation for the reduction of manganate 7. So now that we have the half equations, we can write down the overall equation. Now in the overall equation, remember, the gain of electrons has to be equal to the loss of electrons, right? Because the overall equation, you don't have any electrons. So if each manganate is gaining 5 electrons, that means that, and we know that each iron is Fe2 plus is just losing a single electron. We're going to have to multiply the half equation for oxidation by 5. Okay, so we have 5 Fe2 plus, 5 Fe3 plus, and then 5 electrons. So now we can write down the overall equation. Okay, the overall equation is just the sum of the two half equations. Okay, so now that the electrons are balanced, we can just add the two half equations to get the overall equation. Okay, so if we add the left hand sides of the equation, right, what we get is, we get 5 Fe2 plus MnO4 minus plus 8H plus, right, 5 Fe2 plus MnO4 minus plus 8H plus. So we have 5 Fe2 plus MnO4 minus plus 8H plus. The electrons on the left and the right hand side cancel each other out. So we have 5 Fe2 plus MnO4 minus plus 8H plus gives us Mn2 plus 5 Fe3 plus 4H2O. Okay, so we have 5 Fe3 plus, we have 1 Mn2 plus, and then we have 4 H2O. So here we have the balanced equation for this reaction. Now let's try balancing the exact same equation using changes in oxidation number. Okay, so we have the exact same equation. We're going to balance it using changes in oxidation number, right? Again, if you want to balance it using changes in oxidation number, the first step is we identify the reducing agent and the oxidizing agent. We already identified. So over here we know that the reducing agent is Fe2 plus, right? Reducing agent is Fe2 plus, so it's undergoing oxidation, right? So we identify specifically which atom, right? For which atom the oxidation number is increasing. Over here we know that the oxidation number of iron atoms is increasing, right? Or iron is increasing from +2 to +3, right? It's a reducing agent, it's undergoing oxidation. Similarly, when we look at what's being reduced here, right, the oxidizing agent, that's manganate 7, and specifically the oxidation number of manganese is changing, right? It's decreasing. So the oxidation number of manganese is decreasing. It's going from +7 to +2. So what we can say here is that the change in oxidation number for iron is +1. The oxidation number is increasing by 1. And the change in oxidation number of manganese is -5. It's decreasing by 5. And we know that the changes in oxidation number have to cancel each other out. Okay, they have to balance out. So if each manganese atom, the oxidation number is changing by -5, that means that we're going to need 5 irons, right, to balance the change in oxidation numbers. Okay, again, so over here the increase in oxidation number has to be balanced with the decrease in oxidation number. Okay, since manganese, okay, or manganate 7 wants 5 electrons and each iron is only giving it 1 electron, we need 5 irons or 5 Fe2 plus for every 1 manganate 7. So we can say that we need 5 Fe2 plus for every 1 manganate 7, right? So over here then, if we just balance the rest of the equation, we have 5 Fe2 plus on the left, we're going to have 5 Fe3 plus on the right, we have 1 MnO4 minus here, so we're going to have 1 Mn2 plus, right? And then we have 4 oxygens on the left, so we're going to need 4 oxygens on the right, so that's 4 H2O. And then we have 8 hydrogens on the right, so we're going to have 8 hydrogens on the left. So this is the overall equation. So this method is a lot simpler than using half equations. Here, what you have to do is you just first have to identify specifically which atoms are being oxidized, right? Or the oxidation number is increasing for which particular element, and you have to identify for which particular element the oxidation number is decreasing. And you just have to balance the changes in oxidation number. So over here we identified that we need 5 iron for every 1 manganese. Okay, and then we can balance the rest of the equation. So now let's look at the next equation, okay, that we have to balance. We have zinc reacting with acidified iodate 5 ions, okay, to form Zn2 plus iodine plus H2O. We just have to balance this equation, and we're going to balance it using changes in oxidation numbers. Now here again we have a redox reaction, okay. Zinc is the reducing agent, right? It's undergoing oxidation, right? It's undergoing oxidation from 0 to +2, and iodate 5 is the oxidizing agent, right? It's undergoing reduction, right? It's undergoing reduction. Now in iodate 5, the oxidation number of iodine is just +5. You can calculate that as well. If we have IO3 minus, we can say that the oxidation number of iodine is, let's say, X, right? We have 3 oxygens, each of which is -2, and the overall oxidation number is just the charge, which is -1, right? So we get X is equal to +5. So what we can see here is that the oxidation number of iodine is decreasing, okay, from +5 to 0. So iodate 5 is the oxidizing agent, right? It's undergoing reduction. The oxidation number is decreasing. Now we've already identified the oxidizing and the reducing agent, right? So when we're going to balance this equation, we're going to say, okay, we know what's being reduced, right? That's the oxidizing agent, and specifically over here, the oxidation number of iodine is decreasing, okay? So we've identified which particular atom the oxidation number is decreasing for, right? We know that the oxidation number of iodine is going from +5 to 0, right, in the elemental form. Similarly, we've identified what's being oxidized, right? Here zinc is being oxidized, and the oxidation number of zinc is going from 0 to +2. So we can say that the change in oxidation number of iodine is -5, right? The oxidation number is decreasing by 5, and the change in oxidation number of zinc is +2. It's increasing by 2. So again, since the changes in oxidation numbers have to be balanced, right, we can say that for every 2 iodine atoms, we're going to have 5 zinc atoms, right? They're reacting in a 2:5 ratio, right? 1:2.5. So for every 2 iodine atoms, you're going to need 5 zinc. So we're saying that 2 iodine atoms, the oxidation number will decrease by 10, and the 5 zincs, the oxidation number will have an overall increase of 10, right? +10. So the overall change in oxidation number of 5 zincs is +10, and the overall change in oxidation numbers of 2 iodines is -10. So we can balance this equation, right? We said that for every 5 zincs, we have 2 iodines. So over here we have 5 zincs. So here we have 5 Zn2 plus, right? We have 2 iodine atoms on the left. So we're going to have 2 iodine atoms on the right. That's just 1 I2, right? Then we have 6 oxygens on the left. So we're going to have 6 oxygens on the right, right? So 6 H2O. And now we have 12 hydrogens here. We're going to have 12 H plus. So that's the balanced equation. So now let's look at the next example, okay? So the next equation that we have is the following. Okay, we have potassium iodide reacting with sulfuric acid, H2SO4, okay, to form potassium sulfate, iodine, hydrogen sulfide, and H2O. So here we have the unbalanced equation for this reaction, okay, and we want to balance this equation, and we're going to balance it using changes in oxidation number. So the first thing we do here is we identify the oxidizing agent and the reducing agent, right? Over here, iodide is the reducing agent because iodide is being oxidized, right? The oxidation number of iodine is -1 here, right? And I minus, and then an iodine is 0, okay? So potassium iodide is the reducing agent, right? Undergoes oxidation, which means that sulfuric acid is the oxidizing agent. It undergoes reduction. So now that we've identified the reducing agent and the oxidizing agent, okay, we're going to try to balance this equation by looking at specifically for which atom the oxidation number is increasing. Over here, we know that the oxidation number for iodine is increasing, right? Because we can see that iodide over here is -1, and then in iodine in the elemental form it's 0, right? So the oxidation number of iodine is increasing from -1 to 0. We can also see over here that the oxidation number of sulfur is decreasing. Okay, now over here we have sulfuric acid. Okay, and if we have sulfate, okay, the oxidation number of sulfur is +6. You can calculate that as well. If we have H2SO4, we have 2 H pluses, right? That's 2 times +1. We have 1 sulfur, let's call that X, and we have 4 oxygens, each of which is -2. The overall oxidation number is 0, so it's a neutral compound, which gives us X as +6. Okay, so the oxidation number of sulfur in sulfuric acid is +6. We have the same oxidation number in potassium sulfate. So here the oxidation number is remaining unchanged, right? The same sulfate that we have here, the +6, we have that +6 here. However, in H2S and hydrogen sulfide, the oxidation number of sulfur, okay, in hydrogen sulfide is -2, right? We have 2 hydrogens which are +1 each, and sulfur which is X, right? So we know that X is equal to -2. So what we can say is that sulfur, the oxidation number is decreasing from +6 in sulfuric acid to -2 in hydrogen sulfide. Okay, so what we can say here is then that the oxidation number of sulfur is decreasing. So what we can say is that the oxidation number of sulfur is decreasing from +6 to -2. So now we can say that if we look at iodine, the change in oxidation number is +1, right? It's increasing by 1. And for sulfur, the change in oxidation number is -8. It's decreasing by 8 from +6 to -2. So then what I can say is that for every sulfur atom that is reduced by 8, right, or for every sulfur atom for which the oxidation number decreases by 8, we need 8 iodine atoms. We need 8 iodine atoms for which the oxidation number increases by +1, because the overall increase in oxidation numbers has to be equal to the overall decrease in oxidation number, right? So here what we're saying is that for one sulfur to gain 8 electrons, okay, and decrease its oxidation number by -8, 8 iodides would have to lose a single electron. Okay, so that means that for every single iodide, okay, the oxidation number increases by +1. So for 8, we have an overall increase of +8, and that balances the overall decrease in the oxidation number of sulfur, which is -8. So from this we can say, okay, we have 8 iodine atoms being oxidized for every 1 sulfur atom that's reduced, right? Now, we're not going to balance on this side, because here the sulfur is going to 2 different places, to potassium sulfate and to hydrogen sulfide. We're only concerned with the sulfur that's being reduced. So we're only looking at this sulfur, right? And we're saying that for every 1 sulfur that's reduced, 8 iodine atoms are oxidized. 8 iodine atoms being oxidized would mean we have 8 Ki and 4 I2, right? So we have 4 I2. That's 8 iodine atoms, right? 4 times 2. So now we can balance the rest of this equation, right? We have 4 I2 here, that's 8 iodine, so we have 8 Ki, right? 8 Ki. Then we have 8 potassiums here, so we're going to have 4 K2SO4, so that we have 8 potassiums on the right hand side. Now on the right hand side, we have a total of 4 plus 1, 5 sulfur atoms. So on the left, we would also have 5 sulfur atoms, so that's 5 H2SO4. And then on the left, we have a total of 20 oxygens. On the right, we have 16. So we're going to need 4 more, so we're going to have 4 H2O. Okay, so this is the balanced equation. The next example that we have is the reaction of sodium hydroxide, okay, hot sodium hydroxide with chlorine. Okay, so we have chlorine. It reacts with hot sodium hydroxide, okay, NaOH aqueous, okay, to form sodium chloride, sodium chlorate 5, that's NaClO3, and H2O. And again, we have to balance this equation. Now over here, what we notice is that chlorine is being both reduced and oxidized, okay. So this is called a disproportionation reaction. Okay, it's called a disproportionation reaction. We just defined that. What we see is that the oxidation number of chlorine in the elemental form is 0, right? Over here, the oxidation number is 0. In sodium chloride, we have chloride, so it's -1. And in sodium chlorate 5, as the name suggests, it's going to be +5. Okay, we can calculate this. Sodium is +1. Let's say chlorine is X, and we have 3 oxygens, each of which is -2, and the overall oxidation number is 0. We get X is equal to +5. Okay, so the oxidation number of chlorine here is +5. So then what we can see here is that the oxidation number of chlorine is decreasing from 0 to -1, and it's also increasing from 0 to +5. That means some of the chlorine atoms are being reduced and some of the chlorine atoms are being oxidized. So if we look at the chlorine atoms being reduced, right, we know that the oxidation number of chlorine, okay, in the elemental form is 0, and in sodium chloride is -1, right, so it's decreasing by 1. So we have a change of -1. And now we're going to look at the chlorine that's being oxidized, right? The chlorine that's being oxidized, we have the oxidation number of chlorine increasing. Okay, we have the oxidation number of chlorine increasing from 0 to +5. Okay, so we have a change of +5, right? We have an increase of 5. So over here, okay, we can say that for every one chlorine atom that's oxidized, 5 of them will be reduced, right? Again, because the changes in oxidation number have to balance, right? So for every one chlorine atom that's losing 5 electrons, 5 will gain 1 electron each. So then we can say that for every one chlorine atom that's oxidized, right, for every one chlorine atom that has an oxidation number of +5, 5 of them will have an oxidation number of -1. So now we can balance the rest of the equation, right? On the right hand side, we have a total of 6 chlorine atoms. So on the left, we'll have 3Cl2, right? That's 3 times 2, that's 6 chlorine atoms. Now on the right hand side, we have a total of 6 sodium atoms, right? 5 plus 1, 6. So we're going to need 6 sodium atoms on the left. So that's going to be 6 NaOH. And then we have 6 hydrogens on the left. So we're going to have 6 hydrogens on the right. So that's going to be 3H2O. So this type of a reaction is known as disproportionation. Okay, disproportionation. Okay, a disproportionation reaction is a reaction in which, okay, a reaction in which a single substance / species undergoes both oxidation and reduction. Okay, or you can say is both oxidized and reduced. Okay, undergoes both oxidation and reduction. Okay, or you can say it's oxidized and reduced simultaneously. Okay, both under oxidation and reduction simultaneously. So over here we can see that this reaction may be referred to as the disproportionation of chlorine, because chlorine is being oxidized and it's being reduced. Some of the chlorine atoms are being oxidized and some of the chlorine atoms are being reduced, but from the same reactant. All right, so over here, right, we can say that for every 5 chlorine atoms that are reduced, one of them is being oxidized. Okay, so let's look at one more example for a disproportionation reaction. Okay, we have the following reaction. Nitrogen dioxide reacts with H2O, okay, to form nitric acid and nitrogen monoxide. So this reaction, okay, is the disproportionation of nitrogen dioxide. Okay, over here nitrogen dioxide is undergoing disproportionation. Specifically, over here we can specifically say that some of the nitrogen atoms, right, the oxidation number is increasing, and for some of them the oxidation number is decreasing. Okay, over here the oxidation number of nitrogen is +4. Okay, in nitric acid, right, the oxidation number of nitrogen is +5. Okay, because we have the nitrate ion, right? Again, remember, hydrogen is +1. Let's say nitrogen is X, and we have 3 oxygens, each of which is -2. Overall is 0, so X is equal to +5. Okay, so the oxidation number of nitrogen is +5 in nitric acid, and then the oxidation number of nitrogen in nitrogen monoxide is +2. Right, since oxygen is -2. And here again, oxygen is -2, so that's 2 times -2, that's -4, and nitrogen is +4. So over here, Okay, again, we can say that this is disproportionation of nitrogen dioxide. So some of the nitrogen atoms are reduced, okay, from +4 to +2, right? That's a change of -2, right? The oxidation number is decreasing by 2, and some of the nitrogen atoms are being oxidized, right, from +4 to +5. So that's change in oxidation number of +1. So here we can say that for every 2 that are oxidized, right, for every 2 nitrogen atoms for which the oxidation number will increase by +1, right, one of them will be reduced. So here we can say that for every 2 that are oxidized, right, so that is for every 2 nitrogen atoms that are oxidized, right, that's in nitric acid, right, we're going to have 1 nitrogen atom that is reduced. So we're going to have 1 nitrogen monoxide. Then we have 3 nitrogens on the right hand side, right? We have 2 plus 1, 3. We're going to have 3NO2. So now this equation is balanced, right? We have 2 hydrogens on both sides, and we have 3 times 2, 6 plus 1, 7 oxygens on the left, and we have 7 oxygens on the right, right? 2 times 3 plus 1. So this is how we can balance this equation.